All right, this video is going to be on continuity and differentiability. These are major topics in calculus, and we really are just going to skim the surface of it, and I think that's good enough for what we're doing. So let's get started. Continuity. I've got 5 examples here, and only one of them is continuous at a particular value of a. Which function is continuous at a? If you said graph 5, you are correct. The other functions are not continuous at a. You can see here that there's a jump discontinuity. You can see here at a, it's actually an asymptote and it never touches a. Here we have a hole, so it's not continuous. And here we have a hole with a point above it. We actually call that a removable discontinuity. So the 4 graphs, these 4 are not continuous. What is a kind of informal way of saying that something is not continuous? Well, we could say that it has a jump. It has a hole, maybe an asymptote. We can think of it as not being connected. Being connected. I tried to save that, didn't work so well. I'll erase it. Being connected. Okay, so those are not continuous because there's some sort of jump, hole, asymptote, and they're really not connected at that particular value. Here, it is connected. This is very informal, right? We can see that this whole graph is connected. In fact, because of these arrows here, we could actually say that this function is continuous for all values of x. What's the formal definition of continuity? Well, here it is. You might want to pause your video and get this down. Continuity as defined by limits is basically saying that all 3 things have to be true. But if any one of those conditions is not met, then the function is not continuous. So let's do an example here of one that works. Let's do, is the function continuous at x equals 0? That's the question. Well, let's do all 3 of these things. Is f of 0 defined? Sure, f of 0 is equal to 1. What's the limit as x approaches 0? Well, that's also 1, right? From the left, it's 1. From the right, it's 1. And are both of these 2 things equal, right? They're saying, are these 2 things, problems 1 and 2, are they equal? Well, are those equal? Then yes, they are. Yes, they are continuous. So in other words, the limit has to be the same thing as when you evaluate that function at that particular point. And that makes sense. All right, let's try one where it doesn't work. So let's find, how about x equals minus 2? All right, what's the limit? Oop, I skipped one. Let's go back and do number 1. What is f of negative 2? Well, f of negative 2 is actually 2, right? Because this is filled in right there. What's the limit as x approaches negative 2 of f of x? Well, that does not exist, right? One is coming from the left is 2, the one that's coming from the right is minus 1, so that does not exist. So does my limit of does not exist equal 2? No, of course not. So these are not equal, so these are not continuous. I'm not going to emphasize that too much. What I really want you to be able to do is identify that these 4 are discontinuous and then this one is continuous at x equals a, and for all values as well. But that is the formal definition of continuity. It combines limits as well as evaluating a function. How else can you figure out if something is continuous? Well, you can just plug right in. Is f of x continuous at x equals 2. Well, let's see. Let's plug in 2. F of 2 is equal to 2 squared minus 1 over 2 minus 1. Well, that's 4 minus 1 is 3 over 1 equals 3. So that value does exist, and if we were to look at the graph, you would see that there is a limit. But for the most part, when you plug straight in and you get a value, you would say, yes, this is continuous. Continuous at x equals 3. Let's try a different problem. Let's try x equals 1. Oopsie. X equals 1. Well, let's plug it in. So we get f of 1 is equal to 1 squared minus 1 over 1 minus 1, which is equal to 0 over 0. That's a problem, right? We can't have a 0 in our denominator, so this function is not continuous. And the reason why is there is no function value. There's no function value at x equals 1. And that would be a great answer. I would totally accept that. Let's go ahead and let's look at the graph of this. Whoa, that didn't work. You can see here that at x equals 1, we have a discontinuity. The function is not continuous at x equals 1. However, at x equals 2, right here, the function was continuous, as you can see. All right, I think I'm going to pause this video and not do differentiability with continuity. It's already been long enough. Thanks for focusing, and thanks for being great.